Welcome to the webinar Non-Sequential Physical Optics. My name is Huiying Zhong, come from Lighttrans International. In the latest released version of VirtualLab Fusion 7.3, one most important new feature is the non-sequential modeling. In this webinar, we will show how to use this feature. Before we start, users may know that the non-sequential extension is a program in VirtualLab Fusion, and the users need to buy the related license for it. To obtain the purchase information, please contact your local distributor. You may find the distributor information online. Let's start with the question, what is sequential and non-sequential tracing? When model an optical system, users first define the source, different components, and detector. Then light propagates from source through different components one by one until detector. It means that users have predefined the sequence of components, and the light propagation follows this sequence. It is sequential modeling. As an example, we would like to collimate a high-NA laser beam by using this collimation lens system. There are 3 lenses, more specifically 6 optical surfaces. Light propagates through surface one by one from 1 to 2 until 6, sequentially. This is sequential tracing, and you can see both sequential retracing and sequential field tracing results here. In the detector, we can see a very smooth distributed intensity. Of course, it only happens when all the surfaces are well coated by using perfect anti-reflection coating, so the reflection light from each surface is really marginal and we can neglect them. Then sequential modeling can be used here. But sometimes it also happens, for example, here the surface 4 and 5 are not well coated. So light comes to surface 5, may reflect and hit surface 4 again, and the reflected light goes to detect also. We can see now the detected field shows a slight interference pattern. This is interference pattern between the directly goes through light and the reflected light from surface 4 and 5 and transmitted. We can see now the light propagation doesn't really follow the sequence we predefined. It may have multiple reflections between surface 4 and 5, or we can see light comes to surface 4 and 5 several times. This is what we call non-sequential tracing. Here we also show the results of both non-sequential retracing and non-sequential field tracing. In the demonstration slides, light propagates not follow the predefined sequence, but find its own path, and may come to one component several times. It is non-sequential modeling. Conclusion for the first question, what is sequential and non-sequential tracing? In sequential tracing, users may predefine the sequence of components, and the light propagation through these components follows that sequence. Generally, light propagates through or reflects from one component just once. But in non-sequential modeling, light propagation doesn't follow any predefined sequence. Light defines itself which is next component it will go. Generally, light may propagate several times through or reflect from one component. But note, here we can also see some sequence of the component. This sequence shown here is only used for positioning. You will see some examples later. Now let's come to the second question. How to enable sequential and non-sequential modeling in VirtualLab Fusion? Here we take advantage of a channel concept. In each optical surface or component, we can define different channels. By correctly defining the channels, we could enable sequential and a different degree of non-sequential tracing. We will use these figures to illustrate the concept of channels. Here we define one component with 2 surfaces. For both surfaces, we can enable 4 different channels, plus plus, plus minus, minus minus, and minus plus. Now let's see the meaning of different channels. In setting A, we just enable plus plus channel for both surfaces. Plus means the propagation direction of light is along positive direction. The positive direction of z-axis, but not this z, but the z-axis of local coordinate system of this surface, as shown here. In VirtualLab Fusion, each surface or component has its own local coordinate system. Users may see them in 3D view window. Again, plus means positive direction along z-axis of local coordinate system of the surface. Here, plus plus. First plus means the direction of incident light, and the second one means the output light. So plus plus means incident light propagates along positive z-axis, while output propagates also along positive z-axis. So this is a transmission channel. For the second surface, everything is the same. In the setting B, we open plus minus channel of the first interface, which means input propagate along positive z, while output propagate along negative z, so it is a reflection channel. For setting A and setting B, although the output light sometimes split into two fields, two modes, reflection and transmission, but the input light just come to each surface once. Light firstly come to the first surface and then second, follows the simple sequence. So both of A and B are still sequential tracing. In setting C, we enable the reflection channel plus minus of the second interface, so propagate positive and the output propagate negatively. While for the first interface, we enable another channel, minus minus. So the input beam propagate along the negative z-axis, output beam also. It is again a transmission channel, but the input comes from the behind side. It means light propagates through first interface and reflects from the second one and goes back to the first interface again. Light comes to the first surface twice. It is already a non-sequential modeling. In setting D, we would like to calculate the reflection from the double interface component with considering the multi-reflection between the two surfaces. So we can see when the incident light comes, we calculate the transmission of the first surface is plus, plus, and the light come to the second surface reflected, so it's plus, minus, and then the reflected light come to the first interface again. It is split into two fields. One is transmitted, minus, minus, another field reflected, it's minus, plus. So incident come from the second surface, so it's propagate along the negative z-axis, but the reflection propagates along the positive z-axis, so it's minus, plus. Light comes to the second surface again. Finally, for the first surface, we enable plus plus, minus minus, minus plus channel. While for the second surface, we just enable this reflection channel plus minus. Of course, you can enable all the channels for both surfaces. Then both reflection and transmission of this double interface component with considering multi-reflection can be calculated. This is setting E. This is a 4 degree of non-sequential tracing. Till now, that is all for the channel concept. The channel concept gives quite large benefits. It's quite convenient to use, and switching between sequential and different degree of non-sequential tracing is quite flexible. We just need one optical setup, for example here a double interface component, and switching between sequential and different degree of non-sequential tracing by defining different channels of both surfaces. Now let's look at a sample. Here we will build up an optical etalon with one cylindrical surface and one planar surface. We don't need to build up this optical system from scratch on, but simply open the sample file vir1etalon from the downloaded folder. Let's open VirtualLab Fusion. First, we can check the licensing information. You can see non-sequential extension in my license is activated. Then from the download folder, drag and drop the file vir1etalon into VirtualLab Fusion. This is the optical setup. It contains one plane wave, one etalon with planar and cylindrical surface, and one camera detector. In the property browser, field tracing second generation, you can see non-sequential tracing here is marked as false. It means that non-sequential tracing is not enabled. Now it's still sequential modeling of this optical setup. If we select Ray Tracing System Analyzer as a simulation engine, you can see light directly propagate through the etalon. We can also check the result of field tracing second generation. This is a detected field in the camera detector. Now we would like to enable non-sequential tracing. For the same optical setup, we just need to change it in the property browser, non-sequential tracing from false to true. You can see several parameters appear. We will show the parameters later. Now let's double-click the etalon. In propagation channels, I also check the reflection channel minus plus for surface 1 and plus minus for surface 2 to enable the multi-reflection between the two surfaces. Click OK. We first check the Ray Tracing System Analyzer. Now the light propagates through first interface to the second. In second interface, light split into two modes. One reflects and the other one transmits. But then, after the light reflects from the first interface, we just find the transmitted light on the surface 2. You may ask me why there is no reflection from surface 2. That is because here we use two parameters to control the iterations or levels of non-sequential tracing. Here, the reflected mode is not shown or calculated because it contains too less energy. This energy is less than 0.01% of the input energy. So it is too marginal and neglected by VirtualLab Fusion. Only this transmitted mode is calculated. The energy threshold is one of the most important parameters to control the numbers or the levels of non-sequential tracing. We can also control the level, non-sequential level by using maximum levels here. For example, we give a very small value, 3. Let's do the Ray Tracing System Analyzer again. Now even the transmitted mode is not calculated. Here's 1, 2, 3, the 3 levels of non-sequential tracing. The transmitted mode will be the first one, but we limit the maximum level number by 3. That's why it's not calculated. There are two parameters. These two are the two parameters to control the non-sequential levels. Now let's change the maximum level back to 100 to make sure the level value is high enough. The non-sequential tracing level is only controlled by the energy threshold. First, check the ray tracing. Okay, the second transmitted mode is calculated again. And now let's check the field tracing second generation to calculate the fields on the detect plane. You see, here is the first transmission mode, and we may have the second transmission mode caused by non-sequential tracing. Here we already see the interference pattern between the two modes, but the second one seems very weak. I mean, the energy of the second transmission mode is quite small. We can use a rectangle marker to mark this part because we guess the second mode should have some field distribution here. And click Selection-based Skewing. It means now we skew the color bar range. The largest value now is the largest intensity value within this rectangle. Now we could see the light distribution of the second mode. But for the color bar now, the first mode is too bright. First mode here, second mode here. The overlap part gives the interference pattern. Change it automatically skewing, you can see. Now the plane wave is linearly polarized along x-axis, so it's EX polarized. Now we change it to EY polarized by setting the value to be 90 degrees. 0, 1 is EY polarized. Calculate the field in detector plane again. We also have two modes with interference pattern. To make these two results comparable, we first rescale color bar of the result with EX polarized incidence by make the rectangle marker larger, selection-based skew, and then use F2 button to rename the window as EX incident. For the one with EY polarized incidence, we click Copy View Settings, choose the EX incident window. Now both windows has the same color bar, but obviously intensity modulation of EY polarized incidence, the interference pattern in the second window, is stronger than the other one. The difference caused by different polarization states in non-sequential tracing is correctly calculated or accurately calculated because polarization is one of the most important properties of electromagnetic field, and we always calculate the electromagnetic fields accurately. From now on, the concept of non-sequential tracing and the channel concept is introduced. Conclusion of the second question, how to enable sequential and non-sequential tracing. For one optical setup, we can set the term non-sequential tracing from false to true, which means now we change from sequential tracing to non-sequential tracing. Then users set the channels of each surfaces or components to define different degree of non-sequential tracing for the optical setup. There are 4 different channels, and we have already introduced the definition of different channels. From now on, the concept part is done. Let's go through some applications which take advantage of non-sequential tracing. Here I prepare 3 examples: telescope, interferometer, and analysis of a ghost image. In the first example, we build up a telescope with 2 spherical mirrors. Input field propagates to mirror 1 and reflects, then propagates to mirror 2 and reflects and propagates to mirror 1 again. So it is a multi-reflection between mirror 1 and 2, and finally the light focused in the detector plane. And we would like to check the PSF distribution in detector. We again come to VirtualLab Fusion. Drag and drop the sample file 02 to VirtualLab Fusion. In Property Browser, non-sequential tracing is enabled. We first check retracing system analyzer to see how light propagating through the telescope. It is exactly similar with what we described in PowerPoint. Light propagates between M1 and M2, mirror 1 and mirror 2, and finally come to detector. Let's guess how to define the channels of mirror 1 and mirror 2. For M1, enlarge a bit, we can see the coordinate system. This is z-axis. Light comes from the front side, propagate along positive z, and reflects, propagate along negative z. So it is a plus minus channel. Then move to M2. Also enlarge it and see the coordinate system z-axis. Although it seems like the light comes from the behind side, but in fact, compared with the direction of coordinate system of M2, the direction of light from M1 is propagating positive along z, and then reflect from mirror 2 and propagate along negative z. So this is also a plus-minus channel. Be careful, our reference coordinate system of channel definition is always local coordinate system of the surface or components, but not the global one. Whenever users identify the local coordinate system of the components, channel definition becomes quite easy. Now let's simulate light propagation by using ray tracing. This is a recommended workflow from us. First, use ray tracing system analyzer to have an overview of light propagation in system, and then using ray tracing to calculate the dot diagram in detector. It is used to define the interesting screen size. In spot diagram, we mark a rectangle by rectangle marker, and now we would like to calculate the field within this rectangle. Right-click the detector. Copy detector window from the dot diagram. Now let's use field tracing second generation. We can see within the rectangle, field looks like this. Because of diffraction, field distribution is larger than the ray spots. So let's enlarge the detector size to be 50 by 50 microns. Double-click the detector. Here we input 50 micron by 50 micron. And run the simulation again. Now we can see an error pattern. Simulation is quite fast, just several seconds. Then let's think about if incident light is inclined, what happened. Here we give result figures when incident direction changing from 0 degree to 0.6 degree, 0.6 degree. Angle changing is in three-dimensional space. That's why we have two values. Now we don't do all, but just do the last one. In VirtualLab Fusion, the angle can be defined in plane wave. Double-click the plane wave. In spatial parameter, let's change the angle to be 0.6 degree, 0.6 degree, and click OK. Now we need to go through the workflow again. But first, let's remove the size of detector window and set it as automatically. First, we use ray tracing system analyzer. The changing is quite slightly, it's not obvious. Then perform ray tracing. And use rectangle marker to select the area. Right-click the detector and copy the window of dot diagram. Then we perform field tracing second generation. This is the PSF when the incident light inclined. The calculation takes just a second. This is the first example I want to show. In fact, here I still want to show the channel definition. We must firstly identify the z-axis of local coordinate system of each component, define the direction, and then define the channels. Although this setup looks quite similar with Etalon, but because of the local coordinate system, the mirror is opposite. The channel definition is not the same with Etalon. Now let's move to the second example, Michelson interferometer. In a Michelson interferometer, The Gaussian beam is splitted and propagate to two mirrors, one planar mirror and the other one is a sample mirror to be measured. Here we use a spherical mirror with a minus 10 meter radius. The light reflected by these two mirrors. This reflection propagates through the beam splitter, while this one reflects from the beam splitter. Now, in fact, when the reflected beams come back, the beam splitter performs as a beam combiner. Then we would like to see the interference pattern in detector. Taking advantage of non-sequential tracing, the setup of a Michelson interferometer can be very compact. In VirtualLab Fusion, it looks like this. Gaussian beam splitter, two mirrors, and a detector. Non-sequential tracing is enabled, very compact. Let's first perform a retracing system analyzer and check light propagation as we expect. Then field tracing second generation, we get the interference pattern. It just takes 1 second, very fast. But here I want to see one more sentence. For the users who do not have non-sequential extension, interferometer can also be set up and simulated accurately. But as in sequential tracing, light cannot come to beam splitter twice. We need to set sequentially another beam combiner in the optical setup as here. So the light path looks a little bit more complex than the non-sequential one. But again, in interferometer, although light comes to beam splitter several times, but the light path is easily to predict. So we could still use sequential mode, just the light path is a bit more complex. Let's also run retracing system analyzer and field tracing second generation. We also get the same result in seconds. So for interferometer modeling, both sequential and non-sequential can be used, but non-sequential extension makes the optical setup more compact. This is one benefit of non-sequential extension. Then we come to the last example, ghost image analysis. In fact, we have already seen it during the introduction part. The high NA beam is collimated by the 3 lenses system. We first assume surface 4 and 5 are not coated, so multi-reflection may appear here, and calculate the image in the detector. So for surface 4, light comes from behind the side and reflects, so it's minus plus channel. For surface 5, it's a reflection channel, but the incident comes from the front side. Let's come to VirtualLab Fusion and open sample 04. First, double-click the collimation lens. In propagation channels, we would like to enable reflection channel of surface 5 plus minus and the reflection channel surface 4, but the incident comes from behind, so it's minus plus. We follow the workflow. First, retracing system analyzer to get an overview of how light propagates through the system. We can see rays reflection from 5 and reflect again from surface 4, transmitted through the subsequential lens. Come to the detector. Then, using retracing to see the dot diagram in the detect plane. In fact, I'm not quite interested in all areas, so I just mark the central part and copy it to detector. Now let's perform field tracing second generation. You can see the calculation is done very fast. Again, in the center, we can see interference pattern. This is interference pattern between several transmitted modes. After that, we can also check the sequential tracing. Assume all surfaces are well coated, so we don't consider the reflection at all. two ways to do. The easiest way is setting the term non-sequential tracing to be false. Of course, we can also uncheck the two reflection channels in the component propagation channels. Run field tracing second generation. Compared with the previous result, now the intensity is quite smooth. No ghost image at all. Let's summarize the usage of non-sequential modeling. There are different needs for non-sequential modeling. First kind of need is for evaluation of undesired reflection, for example, ghost image or street light, any back reflection between different surfaces in a system. Another kind of need is for simulation of intended reflections, for example, the ones with splitted light paths such as interferometer, or systems with folded light paths, for example, telescope, light guide, prism, or etalons. Non-sequential modeling in VirtualLab Fusion gives the following benefits. It makes the optical setup more compact, as we have already shown the interferometer example. Simulation field is also very accurate with considering all the field properties, for example, polarization, diffraction, coherence, and very important, all the calculates are still very fast. You may feel that all the simulation we show today just takes seconds. And finally, thanks to the channel concept, for just one optical setup, switching between sequential and non-sequential mode is very flexible. Let's conclude the webinar today. In this webinar, we introduced the non-sequential extension in the recently released version VirtualLab Fusion 7.3. If one needs to use this extension, you need to purchase it from the related distributor. You can find the information of distributors on the website LightTrans. Today we introduce how we define sequential and non-sequential tracing. In sequential tracing, light propagates follow the predefined sequence, while non-sequential tracing, light may find its own way. Then, we also introduce how to enable sequential and non-sequential tracing in VirtualLab. We use channel concept. We can always define the 4 different channels on each surface or component, plus, minus, plus. And the definition of different channel is depend on the z-axis of a local coordinate system of surface or component, not the global one. And very important, channel concept makes the definition of sequential and non-sequential very flexible. So we just need one optical setup and we can easily switch in between sequential and non-sequential modeling. Thank you for taking part in this webinar. If you have further questions, please don't hesitate to contact us.